Let's take a look at the final review problem set for Chapter 5. It deals with quadratic functions and factoring quadratic expressions. We first have here the quadratic function in standard form. Y equals ax squared plus bx plus c. That is our standard form quadratic expression or quadratic function. And just like other functions, it's a basic input-output relationship that produces ordered pairs on a two-dimensional xy coordinate plane. And the coefficients for our quadratic function, the a coefficient, the b coefficient, and our constant, the c value, have different relationships with regard to the parabola that is formed when we graph a quadratic function. Let's take a look at the example. We've got y equals, or f of x equals, it can be written as well, y equals 2x squared minus 4x plus 2. And the first question that's asked here is, does the above graph open up or down? Meaning, does the parabola open up or does that parabola open down? And we can see here that the graph is going to open upward because we have learned that the pattern is that if our a value is positive, if our a value is greater than 0, if it's positive, then that will produce a parabola that opens upward. And we can see here that our a value is 2, so that means our graph will open up. And also our b value is -4 and our c value is +2 as well. Those values will come into play as we learn more things about the quadratic function. One of the most important points of a quadratic function is, of course, the vertex, which is either the minimum or the maximum point of the function, depending on if it opens up or down. Because this quadratic function is going to open upward in this shape here, the vertex of this parabola will be the minimum value. First, let's take a look at the axis of symmetry, which is the x value of the vertex. So we can use the values a, b, and c to find the vertex, and the first step to find the vertex is to find the axis of symmetry. And the formula for the axis of symmetry is here. It is the opposite of b over 2a. So we have those values, and we can calculate, and we see here that our axis of symmetry is equal to 1. X equals 1, which means that the vertical line at x equals 1 will basically split our parabola in half. That's why it's called the axis of symmetry, because all the points on the parabola are symmetrical about the line of symmetry. So once we have our axis of symmetry, x equals 1, we know that that is going to be the input value of our vertex, the x value in the ordered pair of our vertex. To calculate the other half of the vertex of the parabola, we take our axis of symmetry value, +1 in this case, and we can input it back into our original function. And we are basically finding out what the output value is when the input is +1. And we see here, we put it back into our original function using parentheses and order of operations, and our output value is 0, which creates the ordered pair 1, 0 for the vertex of this parabola. We talked about it a second ago. What is the axis of symmetry? And it is essentially the vertical line that goes through the vertex of the parabola. And in this case, that vertical line is x equals 1. And so this is going to be the basic shape of our parabola. And as you can see, the axis of symmetry is that vertical line, usually shown on the graph as a dashed line. So we've got our vertex, but there are, of course, other points and values to calculate before we know the exact shape of the parabola. We know it opens upward, but we do not know exactly in which direction in terms of how wide or how vertical or skinny the parabola will be. So we have some other input values here, and we can calculate basically an input-output table to find other points on the parabola graph. You can see here that when -1 is our input, our output is +8, and this work is shown here on the right. When the input value is 1/2, the output value is also 1/2. When the input value is 1, once again, the output value is 0. That is essentially our vertex, so we're proving that that is true. And when the input value is 2, the output value is also 2. Again, using parentheses for our x input values and showing our work using order of operations, we can see the algebraic work that's done here to calculate those ordered pairs. We can then graph our parabola, shown on the next page. So we have our vertex, 1, 0, and we have some of those points that were just calculated. For instance, -1, 8 is here. Again, our vertex of 1, 0 is here. And I want to point out the symmetrical nature of the parabola. So we calculated the point 2, 2, which is shown here. Notice that the point 0, 2 is also a part of this graph. And that goes to show that the c value of our quadratic function, which is +2, also acts as our y-intercept. So the c value of a quadratic function is also the y-intercept, and that's why the point 0, 2 is also a part of this graph. So now we've got the axis of symmetry, we've got the vertex, and we have the exact shape and nature of the parabola opening upward. Staying with quadratic expressions, we have the ability to expand two binomials to create a quadratic expression, and we also have the ability to factor quadratic expressions. We can see here we have two binomials, and we can either use what is known as the FOIL method in terms of first, outer, inner, last, in terms of that multiplication process, or we can understand that we are basically just using the distributive property twice, and that is the case for both of these examples. So we can either understand it as the FOIL method when dealing with two binomials, or we can understand it as the distributive property twice, and each time we'll create a quadratic expression here in the form ax squared plus bx plus c. We can also work backwards, where we start with a quadratic expression and we factor that quadratic expression into its smaller parts. Again, if you have a quadratic expression such as these two examples here, where your a value is 1, there is a specific pattern involved, and that is we are looking for two values that combine to the b term, in this case -5, and multiply to a times c. Our a is 1, our c is -6, so we're looking for two values that combine to -5 and multiply to -6. And we can see here that those two values are -6 and +1. The same goes for this quadratic expression here. We're looking for, since our a value is 1, two values that combine to +2 and multiply to -35. And when we take the factors of 35, we can see that +7 and -5 are the two values that make both of those situations true. Lastly, we move on to a word problem to try to apply some of the knowledge of quadratic functions. In this word problem, it says the engine torque, which is our y value, our output. So the engine torque of one model of car is given by the following equation, where x, the input value, is the speed of the engine. And we have the quadratic function here. The output torque equals negative 3.75 x squared plus 23.2x plus 38.8. Again, this is in y equals ax squared plus bx plus c. It's just that our coefficients are a little more complicated than simple whole positive numbers. Find the engine speed that maximizes torque. So we want to find the engine speed, the input value, the x value that maximizes torque, which is our output value. Since our a value is a negative number, we know that this parabola is going to open downward. So this parabola is going to open downward, and it's going to have a maximum value at the top. This graph is going to come up, reach a maximum height, and then come back down. The question is essentially asking, what is the x value? What is the input value? What is the speed at that maximum point? And since that maximum point of a parabola is simply the vertex, this question is asking us, what is the x value of the vertex? What is the input value of the vertex? And since we know that the input value of the vertex is the axis of symmetry value, we can use our axis of symmetry formula, x equals the opposite of b over 2a, to calculate that engine speed that maximizes torque. I'm using my b and a values in this equation, and we can see that it produces a value of 3.09. That is in thousands of revolutions per minute. That is the engine speed that maximizes torque. The question also is asked, what is the maximum torque? So now that question is essentially asking, what is the output value at the vertex? And just like in our previous example, we can take the axis of symmetry value of 3.09 and input it back into the original function and calculate the output value of the vertex. Again, order of operations, and we can see through some algebraic work here that the output value is 74.68 foot-pounds. That is the maximum torque for this example problem.